Hello. Yeah, Ashish.
Hello.
Yeah.
So shall we proceed?
Yeah,
Okay.
sure.
I hope all the participants will come here
No,
now.
can we wait? I'm ready.
Sir,
No?
you can begin, sir. Sir, you can just begin
Yeah,
within two
fine.
minutes.
Yeah, I will be waiting for another 2 more minutes.
Okay.
Yeah. Yeah. Within
Okay.
2 minutes. After 2 minutes, we'll start. Yeah.
Okay. Sir. Sir, please proceed with the presentation.
Yeah. Okay. Thank you. Thank you, Ashish. Yeah. Yeah.
Thanks.
Yeah. A very good afternoon again for this second session. So this session will be on 3D printing design data file formats. So this is basically um, the major focus will be on the STL file format. So that is the one format which will the 3D printing industry is well adopted right from the inception, means right from the technology started from 1988 onwards till date. STL file is the one file format. So that is made as a de facto standard, but it need not to be the what you call best design format, but still it is going on as a de facto standard. The reasons may be it will be having several advantages, and because of that reason, still it is going as a de facto standard. But still, it have some problems or the challenges that we are going to discuss the problems and the challenges of the STL file format, and of course how that could be addressed by the new file format, the AMF, that is additive manufacturing file format, which is developed by ASTM F42 committee. They have developed this, and then what could be the future of this 3D printing data file formats? So that's what I have planned for this session. And of course, before starting to the STL file, we'll see various design tools that are existing for 3D printing, practice. So, what are the design tools that you can come across? So that is the thing which I'm going to cover these contents during this lecture. So let us start with of course, any 3D printing process. It has to start with the design, the digital design, right? So then that we need to prepare that the digital design for the 3D printing practice. We need to start with that. Of course, as we have already discussed, so rapid prototyping, additive manufacturing, and 3D printing. So you name any, and if you see in the design perspective, so it may be one route, maybe CAD/CAM CAE route, and you have other route, maybe 3D scanning route, and you have the medical data, maybe the another design source. Normally, typically you can come across maybe these are the three, um, say, uh, possible sources of data that we need to start for with the 3D printing. So, so once you get your 3D model, so then that should be data should be converted. So why it should be converted basically? So then you may have several packages. So I may use one package and you may use some other package, and I may use some medical data and somebody else may use some other say reverse engineering or 3D scanning method. So but the source of data may be coming from several sources, but we need to standardize that into a common file format that any 3D printer can understand that file format, and then that could be easily read by the 3D printer. So that's what we need to convert that data. So data conversion should be done, and then it should be transmitted. So the data should be transmitted. Why? Because so you might have collected from some source, maybe some designer or some organization or somewhere else, that design has happened or that data has been generated, and of course we need to transfer that data. Maybe you can use any one of these methods to transfer that data. Maybe digital data you transfer, and as we understood in the previous class also, like we need to start with that model, and then you have some interfacing software with the machine. But that interfacing software, before that the data is sending to that interfacing software, sometimes we need to check the data whether it is correct or not. What do you mean by the say correct data or a watertight model? Normally you call that as a watertight model. What do you mean by that? And if at all, if there are some errors, means you are checking something. So if at all some errors, then how it is getting corrected? So that should be addressed here. So then once you have checked that data and free from errors, and of course we prepare the build setup or the codes to be sent to the machine. So then you perform that operation in the machine, and then you can have the post processing method afterwards also, like to enhance the the capabilities or the properties that you are going to get. Sometimes you may use some UV curable oven for SLA or else basically for epoxy resins, you may use UV curable resins, and that should be 100%. It should be converted as a solid. That's what we need to use some curing oven to make that epoxy resins after building. You may get maybe some kind of a jelly kind of a form, but it should be 100% converted as a solid. So in that case, you may use some UV curable oven. Sometimes you may use ultrasonic cleaning, chemicals you may use, and then you may use some other devices also to do this post processing. So you can see this video like where you have some STL model. So this STL model which you have generated from the any CAD source or any other source, and then at the moment you convert as a STL file, so we can see on the surface all these triangles. So basically it will become as a triangular mesh. So then we need to fix that. Say you have some overhang portion here, so we need to give some support here, right? So then support will vary if you change the build orientation from previous 0 degree orientation to some 45 degree something. You change the orientation, and you can see the amount of material, the support material that is going to consume is different, and the surface finish we are going to get with this orientation and with this orientation is totally different. You have to work on those kind of parameters, and once you are satisfied, and then you slice the data in terms of layers, and once you slice that data in terms of layers, so those layers will be send it to the say your build setup file. In the build setup file, you will be sending that one by one that layers on bottom to top approach, the first layer, second layer, third layer. So like that, all that layers will be this is a kind of a cross-sectional data, normally kind of a G code in case of a CNC. So then you send that data, and then one layer upon other layer, physically it's getting built, and you have the final part that should be you are looking at. So that's what a typical process. And we'll see like we'll focus much on this say file format. So before going to that file format, so you can even start with your 3D model either by capturing, means that is scanning technique. You may have some tools like a Kinet Fusion or a Autodesk recap for reconstruction of your model. Basically, 3D model capture is a reverse engineering approach. So you have some tools to get it reconstructed your say converting your physical object into a digital object. That may be the one route as we discussed previously also. And then CAD design, so that's right from the scratch you will be doing it here. You can use either a blender or a fusion or a mesh mixer, rhinoceros. You have plenty of tools to use this CAD design as route. And then you may have some mesh repair algorithms or mesh repair tools to check your mesh is basically an STL, that is a triangular mesh. So it's only one element here in the 3D printing, that is only the triangle. So you have the triangular mesh repair if required. So it should be getting repaired by using some tools like NetFab or Mesh Mixer, MeshLab or Magix. There's another software. So you can use any one of these say tools to do repair your triangular mesh if required. And then after that you do a slicing of that mesh after repairing. Then we need to slice that model. That slicing will be done in various tools, like it can be a Cura. All these are open source softwares, which I am mentioning almost here. So I will give you a detailed list also about all these tools. So yeah, you can use either a Cura or a Repetitor kind of a say simplify 3D. You have a plenty of tools to do this slicing job, especially for FDM based say technology. It's almost like open source tools available. But still, with the metal and ceramic printing and composite printing, still it may be some proprietary softwares or the tools available. But FDM and SLA technologies are reached to a open platform or a DIY kind of nature. So then you can have these say tools to do a slicing job, and then you may have other source of getting this data is some design libraries, means already somebody has a model and they have kept it in a design library. So then one among maybe Thingiverse. Thingiverse is one say online repository or a digital design library. So you can download these models which are already modeled by some users or some community people. So then even you can make use of them if you could want to use it for the personal usage and research purpose, but not for the commercial usage. But you can use these Thingiverse, maybe one among that. Also, I will give you. There will be several tools available because your 3D printer can able to print in color and different textures, but unfortunately your STL file doesn't support the color and the texture. So in that case, you may use some tools to be something like a Blender software or some kind of a GrabCAD a tool that you can use it to add some colors and textures. Why you want to add that we'll see, and then how do you add, then how do you get that we'll see in the upcoming slides. So let us first discuss on the CAD design tools, which you normally come across. This is going to be the say normal routine interfacing or the start point of your 3D printing. So that should maybe starting with using some CAD tools. So then you start with two-dimensional sketching and three-dimensional wireframe surface and solid modeling you can do. And as far as 3D printing is concerned, better you preferably solid model will be the ideal choice, but surface models also can be accepted by the 3D printer. That should be in STL file format, and it should be free from all opening surfaces or any normals that it got flipped. But anyway, preferably solid model may be the ideal choice for your 3D printing, as we know that it's a complete representation solid model than a surface or than a wireframe model. So then you start getting these CAD models, either any one of these tools available in terms of free form and artistic tools, right from the Blender. So I've given in the bold, those are all open source softwares which you can download as a free of cost, and rest will be maybe the other, maybe the proprietary softwares, and which I am suggesting you as a open source. I made it as a bold, and rest maybe some may be also open source, some may be also the proprietary tools available. And coming to the freeform and artistic, you have Blender, Lightwave, 3D Studio Max, Maya, and you have ZBrush, Sculpt GL for artistic or a freeform kind of nature of your modeling. And coming to the engineering kind of nature, you may have Google SketchUp or a Reno, Mesh Mixer, Mesh Maker, SolidWorks, Inventor, and of course you have AutoCAD, Creo, CATIA. And apart from these, say, tools, even you have OnShape. There is again an open source tool which it can be even running on an Android platform. So you can start modeling your products maybe through your mobile phone or maybe through your tablet or basically an Android based device. Also nowadays it is quite handy to have these kind of tools, of course. So you can use any one of these tools to getting started your 3D printing journey. So under model capture or the reverse engineering or a 3D digitizing practice. So we need to start with the physical object. and then use some 3D scanning or a digitizing, a kind of a touch probe or maybe white light scanner or a laser scanners or a CCD cameras. You may have a different, say, sensors or the scanners based on the property of the object that you are getting scanned. So then you collect the millions of points on the surface of the physical object that you are getting digitizing, trying to digitizing it. So first you will get a kind of a cloud of points. So by touching or by using the lasers, so you can collect these the three-dimensional points or the cloud of points, the coordinates which you can collect, and further you can approximate them with the triangles. Probably you will be calling that as an STL file. That may be the needed format for your 3D printing, or even it can be any other file format like IGS, step, or any other format. It can be saved, and maybe CAE application, or maybe CAM, or maybe now 3D printing. So then you can save this model as a .stl file. So how do you get scanned? Like you can have a physical touching probe, as I discussed, like kind of a stylus ball, or a laser beam kind of scanners, or the scanning device, or it can be a CCD camera. You can see you have some cameras that it is getting captured these images, and then further it can be reconstructed in the software in a three-dimensional solid model or surface model. So, and then you may come across a CT scanners in case of a medical, say, practice. In the medical practice, even you may use some CT scanner. That's also, it will fall under this kind of a capture method. So, means you are not modeling anything here. So, you are capturing or you are digitizing from the existing object. So then you are getting digitized that data. So um, these are some of the digitizing tools or the softwares. You have a Geomagics, you have a Kinet Fusion, Recap, Metashape, and several tools available under this scanning domain. Say, or even you have some specific drone applications. You may have a specific tools to based on your application. So whatever the kind of a tool which you used, the basic idea is to convert or reconstruct your the point cloud data into a surface model, or in total a CAD model that is say input to the 3D printer. So that's the thing where we need to get interfacing your scan data to the 3D printer. You want to modify, you do modifications in these tools, and then you can get it 3D printed. So then you can have a better integration among the scanning technology and the 3D printing technology. You can exploit better benefits. Okay, and you can have even a repository tools, as I said, like somebody has modeled that these models, so maybe and then they are keeping opening, they are going to kept in a community or a digital forum, so where you can be the member of that community, or you can download those say models. So then in this case, if you are looking for some kind of part, so then if it is already there in say in any one of these repositories or a websites, or you can go and maybe become a member, or even without a member also, some of the repositories you can go and download you in terms of STL, or in terms of IGS, or in terms of step, or in terms of part files, native part files from CATIA or from Unigraphics, or any commercial CAD tools. So that native format's also available. So if you are looking for some kind of a professional or engineering applications, which are looking at some standard engineering nut and bolts, or some joints, or some couplings, or some repository. So, and then if you are looking some kind of uh, what you call some hobby sake, some hobbyist models. So then you can go with the Thingiverse. So either if you're looking for some kind of a hobby kind of models, then go visit thingiverse.com. Or if you're looking for some kind of engineering applications, go and become subscribe a GrabCAD community, and then you can see if you are interested. Then you can make use of some of the models that it have been already modeled and kept it in the digital forum. That is another way. And then even you have a medical image processing data and the tools available under this. So we need to know that we need to start with some digital data in case of a medical application of 3D printing which you want to establish. So either you start with an X-ray. Now X-ray digital. Why? Because we need only the digital information. So you start with either a digital X-ray or a CT images or a MRI images going to be the input for your 3D printing machine. But in between, we need to do some processing of this data. So then what we need to do that processing, say, I have the CT scanner and I got the two-dimensional cross sections. Basically, that is a grayscale images. But further, I need to enhance the visibility as well as the. I want to get the three-dimensional. I want to reconstruct from these images, from these layers to a three-dimensional virtual model like this. So, say some COVID patient is there, and you took the CT of that COVID patient chest part, and then which you are looking at the lungs is your region of interest or the organ of interest. So then at that chest part, even you can have the information about the ribs, and you have the information about the lungs and the nerves, spine, but each will be having its a different bone density or a different threshold value normally, or a different Hounsfield value. So then basically this so each tissue or it will be having its own density or its own say number, Hounsfield number. So then based on that you can segment and you can segregate that data as for your say region of interest. So COVID patient, you want to study the lungs, and then you can only take the region of interest as the lungs, and uh, the Hounsfield number or the CT number of a particular organ, which is ranging from so and so Hounsfield, and then you can pick that region of interest. So basically, we need to have some tools to do that job, from raw data from the CT to the machine, the 3D printer understandable language, that is STL, and then we need to do some medical image processing should be done by using these tools. And further, these tools even will allow you to create an interface to your CAD system to modify some implant you have designed. So then further we need to say check that or we need to customize that implant or a prosthetic wherever it is that you are looking at for the particular patient. So then you can create an CAD interface with your medical data, or a surgeon can simulate the surgery once he or she designs some implant, and you have the the data sets that is taken from the patient, and then you have modeled some implant and then testing it fitment, or how do you get fitted this onto the pelvis portion, your femur bone. So then you can do such kind of a simulations on these kind of tools, and further you can generate a 3D computer model, or sometimes an orthopedician wants to do some finite element analysis, or some cardiac or some neurosurgeon wants to do some CFD, computational fluid dynamic analysis. So then you can take these data to that particular domain, maybe FEM, CFD, whichever analysis you want to do it. So then you can take this data, so the patient specific data or the implant which you have designed for the patient. So then you can take and do perform analysis on that. Or further, you can make a physical three-dimensional biomodel and use it for some complex surgeries. So that's what we have been talking about. And then you do some design validations, whatever you have designed, some implant, and then testing it for the validation and testing against failures. Like say, you have an orthopedician has designed some joint, knee joint or hip joint or say a femur joint, femur bone or femur joint, wherever. So then that should be validated before it getting fabricated. So then you can do a design validations on all these tools. So then what are the tools available under this space? So you have software like Mimics from Materialize. And of course, if you are looking for some open source freeware, so then you have a 3D slicer. And of course, you may have other softwares like a 3D Doctor, Simpleware. You have a plenty of tools available. Some may be proprietary, a bit expensive, or maybe less expensive, or a open source or a freewares available under this to getting started your medical data interfacing with the 3D printing. So you can make use of these tools for that purpose. And then we'll come to our actual focus of our talk. Like say, so far we are discussing about, we have several tools or the several methods to get your data, which is fed to the 3D printer, that is in STL file format. STL stands for stereolithography. So that was the first technique developed by Chuck Hull in 1988 with the company called 3D Systems. So that is a STL file journey. I started with a 3D printing journey. It is the STL file. So what is that STL file? We'll see the format of that STL file, how it consists of. So first of all, why we need to have data should be interchanged means you might have used some software like Katia. So you got your data dot part file, but why it is getting converted as a dot STL? So that's simple logic. So how your a domestic 2D printer will understand your PostScript. So that may be either through dot doc or dot pdf or dot jpg or PDF, PPT or any other file format. So, but it should be brought it into the printer understandable post-scripted language or post-scripted format. So, similar way, the counterpart for the PostScript in 3D printing, of course, it may be the STL file. So you have modeled this in an modeling software. So there itself, you have file save as option. So go with the STL. So then that STL can only be read by this printer. But if it is a dot part or dot DWG, so the printer may not be able to understand your so variety of formats. But this is the standard neutral format. So that is meant for 3D printing, or even it can be used STL nowadays. Need not be 3D printing, but it may be the ideal choice for 3D printing application. So which you will be using a triangulated mesh called STL. So then we'll see closely what is an this STL file format is all about. So any 3D design files, so typically it should consist of the data of your CAD model should consist of not only geometry, so it must consist of color, it must consist of texture, and it must consist of material. If you take a three-dimensional solid model, of course, it will be having all the mass properties that a typical, say, a physical object that is having. So, yeah, but unfortunately, your STL file um, does not contain the information about the color, texture and material. It supports only the geometry, means it supports only the coordinates of your triangles. So which you can see, I have some sphere. That sphere at the moment I saved it as a tessellated, nothing but you are discretizing into a triangular mesh. So that is called tessellation. And then that is in .stl file, that is basically a triangular mesh. But this triangular mesh, it is going to be the approximation of your curve with the triangular edge. So again, depends on what could be the chord height or the angle control or the step size. So you can even further improve the resolution of your say mesh. So typically what you do in a FEM mesh also something like that. But here the element is always, it's a fixed, that is a triangular element. Why it is triangle? Why can't it be some other? So of course the triangle is the simplest of all polyhedra. So polyhedra will start with the basic element, that is a triangle, the three sides. And further slicing, next step is slicing. For doing slicing, if it is triangle, so it will be easy to computationally or mathematically, it will be, calculations will be easy, rather than if it is a curve or rather than it is some other shape. That's the logic. You may get doubt why it should be triangle, why can't it be some other element like your FEM mesh. So anyway, so you are not looking at only the representation. So we need to further do slicing, giving some supports or whatever we discussed in the previous say talk, say which we need to do all that stuff. But that will be done on all these steps on this STL file. So, but these old, of course, STL is old and it's very simple format, and which describes the object as a series of linked triangles or tessellated, but no information regarding color, texture, material, file security. But still, if you are looking to support color, so then you may go with the other formats like .obj. So .obj is an object file which it consists of color, texture, and it can be a color, the curves also, which your curves are cutted into approximated into triangular elements. But whereas obj file, it consists of curves and surfaces. We never lose any data once you saved as a obj. And further, if you have the material information that it should be saved, and you may go with the material.mtl files which will support the material information also. So keeping in mind that the ASTM has developed a new file format which is the extension of the STL, as we can say, and which is addressing all these issues that the STL file is not having the color, not having the material, not having the texture, not having the file security, and so on and so forth. So it may be addressed in the .amf. That we'll see in detail what is that. And parallelly, Microsoft is also developed .3mf file format. So nowadays, even you can check these options apart from STL in your CAD tool. Nowadays, with all these current CAD/CAM CAE softwares, you can find even .obj or .amf or even .3mf also nowadays with the new CAD/CAM CAE tools. You can save any one of them, but all the 3D printers can take STL, but not all the 3D printers may not take AMF or 3MF or OBJ or MLT, but all the 3D printers can read .stl file. But still it is an adaptation, depends on the adaptation of these formats is not so great. Because of that reason, maybe still STL file is going as a de facto standard. But anyway, we'll see in insights of these file formats. So what is an STL file? As we are talking about, if you take a typical cuboid, so typical cuboid may be having a 6 faces. On each face, you may have a 2 triangles. That means totally 12 triangles or 12 facets if you take a simple cuboid. So, and if you change your design from simple cuboid to sphere, so you may have a more triangles and you have this form is not a flat in case of say cube, but it is a free form or it's a curvatured one. So you may have a more number of triangles than the 12 number of triangles. It may be thousands of triangles, or it may be lakhs also. Sometimes depends on your resolution which you are going to change. So it may go, and if you take some other geometry, you may have a different sizes and different number of triangles. So your tessellation algorithm will assign will represent the outer surface into triangles. So, and if you closely see that these triangles, if you pick one triangle among these 12 triangles in case of a cuboid, say, and it's a three-dimensional data, and I may have, say, first vertex, so it will be having the x coordinate, y coordinate, z coordinate, and similarly I have the second vertex, vertex x coordinate, y coordinate, z coordinate, and the third x coordinate, y coordinate, z coordinate. Apart from these vertices, and it will be having a normal, so which is perpendicular to this face, or which is perpendicular to the surface. So I have a normal, and again this normal is a vector, so it will be having its normal vector coordinates. So in this way, typically, how many number of triangles it is having? So all that coordinate information about the triangles as well as normal information will be saved in the STL ASCII format. But binary, as we know that it won't be read by us. So it's a machine language. But whereas if you save it as an ASCII format, your STL ASCII format, so it must consist of these coordinate information about each and every triangle. Along with each triangle, there is a normal. So all that information will be saved. So this is a typical STL representation. And then coming to the these STL files, it must have follow some rules. So first rule will be the right hand rule. So what is that right hand rule? Says that so you have triangle, so you may have the sense of rotation. So you may have a two possible say options. Either you can go with the clockwise, or you can go with the anti-clockwise, right? Say even I can go with the say anti-clockwise or clockwise. If I'm going with the clockwise, probably it may be the interior, and if I'm going at the anti-clockwise, so I can understand that that triangle maybe belongs to an external surface, and this is an internal surface. In that way, so your right hand rule will specify whether that is an interior that triangle belongs to an interior surface or exterior surface. And then you have one more rule, or one more requirement that any STL file should satisfy, is the vertex to vertex rule. What do you mean by a vertex to vertex rule? So you have an adjacent triangle, you must have a common say edge, or a common side of these two adjacent triangles. There must be a common side, but it should not be in this way. So then it should follow the vertex to vertex rule. So each triangle must be shared exactly the two common vertices with the each adjacent triangle. So it has to follow these two triangles. And so then you are talking about STL file and the structure, and then why it is still a de facto standard. So then we'll focus some of the advantages of these STL files. So coming to the advantages, the first advantage may be easy conversion. Means, so it is a basically a planar triangle. So it's very easy and it's very simple to contain the list of planar triangles. And it's very easy to convert than any other polygon or any other curve which we are going to represent. So that's a very easy conversion, and you have a wide range of inputs. Means all these CAD/CAM CAE vendors has adopted this tessellation algorithms. The wide popularity or wide adoption of this file format, or the triangulation algorithms, that may be the another advantage of this STL file. Still, it is going as a de facto standard, even though it's not the 100% representation. You have some errors. And simple slicing algorithm. So next step is to slice this data. So the algorithm of the sliced data will be very easy. As I already said, like if it is a triangle, it's a simple calculation involved. The intersection of your slice cutting plane or a slice plane to your triangle. So that is a simple mathematics involved in it, a simple a planar geometry. So then you can find out your slice points. So you can get your coordinates of the slice points where the intersection of your plane with the triangle. So that will be the slicing algorithm will be very simple if we are going with the STL file. And then it can easily split the model. Say my build volume is say 500 by 500 by 500 my printer size, build volume size, and my components is a 1000 by 1000 by 1000 So which I have to split into two halves, and I make separately, and I need to join it. So that may be the solution. Otherwise, I can go with the scaled down version. But I don't want to have the scaled down version. I need to have only 1:1. So then I have to split these models into so the splitting is done very easily if it is an STL file. So these are the some of the advantages which we can talk about the STL files. But what about the problems? If you see the other side of the coin, so what could be the problems that you can understand about the STL files? So these problems may be due to the a triangular boundary representation. So that is, as we already discussed, like it's an approximation technique, approximation solution. It's not exact solution, in fact. So your surface is getting, say, approximated with a triangular edge, as a planar triangular edge. So then it's an approximation. So where your triangular boundary is representing your curve or your any geometry. Every time it is only the triangular facets at the outer boundary. And the problems due to the STL file intrinsic file size, in any one of the CAD tool. So either it can be a B-spline surface or a NURB surface or a Hermite surface, whatever the surface is, some surface which you have model it. So at the moment you save that as an STL file, so your surface is getting approximated into triangles. So basically you are approximating the curved surface with the planar triangles, means where you are losing some data, means you are approximating. In fact, you are not taking the geometry 100% into consideration. Maybe you are approximating it, your curved surface into a triangular edge. And then the file size is too large. Why? Because you have a lot of redundancy, means in terms of vertex, in terms of normals. So there will be a huge redundant data. So that is making a file size is more big. And truncation error, say in the designer, say used your dimension maybe a double precision real number, for example, while designing it. But at the moment you save it as STL file, so your double precision has truncated into a single precision real number. So where you have that say approximating or truncating your double into a single precision accuracy. So that is another problem. And incompleteness, like say it doesn't have any topology information that is got stored. So the connectivity or the associativity don't be there with the say your STL file doesn't have topology, though it have only the geometry, but it doesn't support the topology. That may be the so without topology, so we cannot say it is a complete data. It's an incomplete data. And inconsistency. So this is whenever you have the appending portion, like we said that in the advantage point we have discussed, it can easily split it. Okay, fine, you have split it, but wherever you have that appending of two STL files, so there will be an inconsistency tolerance wherever you have such kind of appendant data. So that may be another issue. These are intrinsic to the STL file format, which you cannot avoid or which cannot minimized. Why? Because this is by syntax and semantics it's going to be. And some inconsistent normals, like the normal should be projecting outside the surface, but some normals may be flipping inside. So which we need to even flip them and orient them into a proper orientation that is outside the surface. Then we need to do some kind of inconsistent normals may you may come across, and incorrect normals also. In normals, you can calculate, reverse calculation you can do, right? So you have these coordinates, and you can even reverse calculate your say normals from your vertex of your triangles. But there will be a kind of so what you call, so there will be a deviation, there will be a different value from this facet vertex to the specified normal. So because of your conversion algorithm may give some incorrect normals also. And then other problems, maybe it is due to the data conversion and transfer algorithms. Say I have some gap, means my model may not be a watertight model. Why it is called as a water, when you can call this a watertight model? So I have one surface here and I have another surface, and if I am dipping this surface, this model into water, and there should not be any leak into this inside the model, means if I am having some triangle got missed at this say interface junction of these two surfaces, say by one triangle, or these triangles got missed. So once you got this kind of a gaps, or the triangles got missed, or the gaps may form. So once you got these kind of problems or the gaps, so if there won't be any gap, and this is an watertight model, while slicing your slicing algorithm, so it will clear cut have the boundary, so where it has to start. For example, so I have started somewhere here, so this is start point, point 1 2 3 4 5 6 7, something like that. So it will, you are going to get a closed boundary, or the contour will be closed if it is free from these gaps. And if there is one triangle got missed and trying to say get a closed boundary, you never get a closed boundary, because why? Because you have missed one triangle here. So then while fabricating this part at this layer, so then how your nozzle or laser has to follow which path? If it is a clear cut closed boundary, so then you can get no, without confusion. So then the filling of the filling algorithm will do a filling job correctly, but otherwise it cannot, right? Say this is another issue, where if you are finding some gaps, or the triangles got missed, and sometimes you may have some internal walls. These walls will be, say you have some internal wall here, and you have one feature, other feature. So rarely you may come across, but there may be some kind of possibility that while designing some problem has come, then it is also reflecting during your STL conversion. And then degeneracy, or like say you may have some degenerate surfaces, surface normals, or the vertices. So you may have, say I have three vertices, but all the three vertices are located at the same coordinate, so which is not contributing any say area of the triangle, right? So in that case, it may call as a topology degeneracy. So it can be say removed. Here you have an extra vertex here. You need only one, but you have three here, and similarly you have two here. So that is called topology degeneracy. So which it can be forming a point or a line. So then that is called a topology degeneracy. And you have some geometric degeneracy also. Though you have an other way around, say you have three vertex, but all three vertex are collinear. So which it is not forming a triangle, but it is forming a line. But you cannot remove this say edge or this any one of these edges. Why? Because you may lost the connectivity of these triangles. So once you do that, so then we need to have some degeneracy in terms of geometry or in terms of topology. So there may be some degeneracies in the STL file. And one more problem is intersection of these triangles, but it should not get interpenetrated kind of triangles. But if at all, if there are some triangles, so you can if you find in your model, so it may be an extra triangle or it is a misplaced triangle. We need to identify and we need to correct it. So then you have some correction algorithms to do this. So this is another problem where you can come across because of your tessellation algorithms or the transfer converting algorithms may prevent some kind of errors to your STL file. So then if it is a valid model, then valid solid model, then you started with the three-dimensional model, and then 2D slicing will be done, and 1D slice, like say your laser will say follow that contour, and it will be filled further by using your filling algorithm or the strategy, the filling strategy, or the tool path that it's going to be filled on it. So if it is a valid model or a watertight model, we can put it in that way. So if it is an error which we have been talking about, there is some triangle got missed and it has formed a gap. So at that gap, while slicing your slicing plane, and then if you are trying to get a closed contour, you never get a closed contour because this triangle got missed. So it would have been a triangle here and it would have been a closed contour. But because of that gap, so then your nozzle getting confused. So then it may say overfill or it may over deposit here. So then finally there may be a build failure or there may be a lot of inaccuracy in your product. So then which we need to focus on these kind of whether the model is a valid or not. So if you give garbage in and you will get only the garbage out, right? Say then one can understand these kind of valid and invalid models we have to analyze. And then the challenges of the STL, like which we are talking about. So duplicated information, leaks, inconsistency, and does not scale well. We have a high resolution and high lattices, and it does not support the color, material, orientation as we previously discussed. And how do you address this with this AMF file format? This AMF file format will address all these. How it is getting addressed, we will discuss one by one. So then basically what is an the AMF file format, the additive manufacturing file format. If you see, this is an XML script. This XML script, so as we understood that an XML script is very easily readable. It's a text based, and you can easily read and you can easily write, you can easily parse, or you can easily edit, and you can easily extendable this format and highly compressive. These are the it's also called as a meta format, a format of formats. So this is an AMF file format if you compare with the STL file. So it also supports a volumetric information, but STL file is not a volumetric data. It is a mesh, a triangular mesh. But whereas here is a volume, it consists of volumetric data, it consists of material information, it consists of colors, and it will also support the grading of the material, like a different composition. Why? Because your 3D printers, some of the 3D printers can print FGMs or the functionally graded materials, and then which we need to represent that in how do you get represented in your CAD file itself, and some lattice, some mesostructures, and even can have some kind of cancellation of the objects, so can easily defined in case of AMF. That we cannot do it in STL file. And how do you get address this kind of say vertex duplication on the leaks of STL file? So then basically it's an XML script which you can easily say read and parse and then do modifications. So then we can identify easily the duplicate or any leaks of the STL file is there. This is a typical STL file which you have modeled it, say AMF file, but whereas which you can easily XML file in format, this is AMF, and then which you can easily do that. Otherwise you cannot, very tedious to read your STL file and identifying these kind of duplicated information or leaks of STL file. And the compressibility also is very good. So if you take a typical ASCII file format, STL file format, consumes say around 800 KB, and if it save it as a binary, so it may have some 200 KB, and if you save it as AMF, it may be between say these two, maybe around 320 or 340 kilobytes of data. And if you try to compress these three file formats, so your ASCII file format will be getting compressed up to 100 KB, and your binary may be around 50, but AMF it can be even further, say 20 or 20, around 20 it can be compressed. So which you can see the AMF compressed is almost less than the binary compressed. So then one can understand the kind of AMF, that how best you can compress the data. And then you are talking about so how your approximation problem will be addressed in your AMF file format. A simple logic, instead of going with the planar triangles, you go with the curved triangles. So that is a solution here, the AMF file format. Instead of a planar patches, you never miss you have some curve. So then that curve is say not say approximated with the triangle. In the curve will be there in the curve. Like why? Because you are using a curved triangle rather than a planar triangle. So then it may be addressed. It's a combination of wherever you have flat surfaces, you can use a planar patches, and wherever you have curved surfaces, go with the curved patches, and wherever you have curved edges, and you can use the curved patch with the edge tangents. So it's a more convenient, but it may be a bit expensive than STL. It's not so simple like STL, but it can be an additional advantage once you work with any complex geometries further without compromising your accuracy. That can be done. And then further, it can be a recursive triangle subdivision, like 4 power n folds. It will be the steps will be further improved to have more resolution of your AMF file format. And this is a typical error that you can compare with the same number of triangles of STL file and the AMF with single fold, means 4 power 0, 4 power 1, 4 power 2, 4 power 3. Like that, if you are increasing the number of folds, so almost negligible error. So zero error almost you are going to get. So that's another advantage where you can improve the accuracy of your part. And how do you address your multiple material assignment? So I have some different material here on this head portion, and this shank portion may be other material. So I can specify this material 1, material 2. So I can easily, so region wise, or I can specify, I can assign a different material to this AMF file format, and even I can grade them. So I can vary the composition from gradiently. So I can do such kind of a thing here. Then I can do different regions, different compositions I can vary, and I can make finally a grading of the material. And I can assign a microstructural, different microstructural structures on it. And then what could be the current status of this AMF file format? So this is under testing, or under not so popularly adopted, but still they are working on to further improving these latest version. So what is that latest version is going to be in a future plans? So they are even trying to add all the product data, like which you will be having some PLM software, or a product life cycle data in a typical CAD/CAM CAE tools which you will come across. So their idea is to have, say, even tolerances also they want to incorporate, and they want to incorporate a surface depth structures, and data inscription, copyrights, and external references, and sub-assemblies, and process controllers, and even non-volumetric supporting structures, or it can be even a non-mesh geometry specific, like it can be a voxel based or a future based representation. They have a lot of plans to be in a single word. We can say it's going to be a complete product life cycle data, which they are trying to incorporate in the future AMF file formats. So then let me summarize what I have done for the last 1 hour, 1 hour 15 minutes. So then we started with an AM file formats, that is STL, and then we have seen the various say advantages, problems, challenges, and how it is getting addressed with the AMF. But I didn't touch up these. These are the other file formats that is for exclusively contour data or like G code, which you are talking about in case of CNC or FDM technology. So then these SLI or SLC, SLI, CLI, RPI, and LEAF, all these, or why you have these many formats? Why? Because you don't have a standard format like STL or AMF in case of a three-dimensional data, but these contour data means after slicing, so you will get a different file formats. All are proprietary file formats specific to a particular company like 3D Systems or Stratasys or US or SLM, maybe other companies that they are developing their own file format. Then there won't be any common file format as like your STL and AMF in case of your cross-sectional data or a contour data. And of course, you may come across other file translators or the formats like IGS, HP, CT, STEP. The idea here is it would have been better if you have some kind of standard data which it can support across all the technologies or all the machines. But that is lagging. But maybe that may be the reason of the proprietariness, or I don't know. But anyway, so you don't have such kind of a that is the state of the art about these file formats. Um, yeah, so okay, then I will be stopping it here. Say then, yeah, before closing my session, so let me give you the facilities that we have at NIT Warangal. So we have a metal 3D printer which is of powder bed system, that is DAP Flex from 3D Systems USA. It can capable of printing in metal material. Say, and then we have the Stratasys make FDM based polymer printers like Dimension, Mojo, Ultimaker, and we have a couple of scanners, and we have a post-processing equipment, muffle furnace, short peening machine exclusively for post-processing for metal 3D printed parts. And we have softwares, 3D printed related softwares like we have Mimics, we have Magix, we have Thematic, we have Catalyst, and 3D Export. 3D Export is a simulation software and the build setup software for metal 3D printer. This is about our facilities at NIT Warangal, and we have an YouTube channel also. If you're interested, you can subscribe. Go to YouTube and you can search EAM Lab NIT Warangal. So you can find a good number of say videos from that YouTube channel. Yeah, then I will be stopping it here, my presentation. So then if you're having specific questions, then I'm happy to answer those questions. So it is over to you, Dr. Ashish, it's over to you.
Okay, sir. Okay. Any queries, please welcome. Every doubt is a genuine doubt. Can you
Anything in the chat box so far?
yes, sir.
Or they can
No, sir.
ask.
As
No.
far as I can see, no queries are there.
Yeah, yeah, fine.
Yeah.
Yeah. Anything they
So,
can ask now also.
yes. No issue, sir. If there is still any query left, then we will discuss it later on.
Yes, yes. Even we have one more session also. Yeah.
Yes, yes,
Yeah,
yes.
fine. Yeah. Yeah.
So, sir, we conclude?
Yeah, yeah, sure, sure, sure. Yeah.
Okay. Sir, thank you. And it will be really a great pride in saying that the knowledge gained in this session gives us confidence. We are heartily thankful to you to share your precious time and your experience from such a busy schedule.
Thank you.
Now we will begin this session on 3 p.m. onwards after having a lunch break. Okay.
Okay,
Thank you,
thank
sir.
you. Thank you. Thank you all. Thank you all. Bye-bye.
Hello, good afternoon. Good afternoon.
Good afternoon, sir.
मैं ज्वाइन कर चुका हूँ और 3 बजे मेरे ख्याल से हमको सेशन के स्टार्ट कर सकते हैं। काफी लोग भी आपके पास हैं, काफी अच्छा लग रहा है, बड़ा अच्छा बनाया है जिसने ये आपका फ्रंट में स्लाइड बनाई है। एक मिनट में फोन कर लूँ, बात करूँ। हाँ, हेलो।
सर म्यूट हो गया।
थैंक यू। नहीं, वो आपका ही फोन था, म्यूट नहीं हुआ तो मैंने इसलिए फोन। हेलो, मैं प्रेजेंट कर सकता हूँ ना?
Dr. Saab, namaskar.
नमस्कार, नमस्कार।
Good afternoon, sir. I will start within 2 minutes.
जी।
About 58 participants have joined. Dr. Deepak Chavda has gone to meet the Dr. Vice Chancellor, sir,
ठीक है, अच्छा है।
for some of the important work, and he has given me this duty to introduce you to our participants.
और अच्छी
Now-
बात है, बहुत अच्छी, so nice.
Ji, Dr. Saab, it's all fruits and blessings of all the legend people like you.
अरे, I'm not, I'm a very ordinary person. I'm learning with them.
Yes, sir.
I'm no better than these participants. I'm also
Yes, sir.
learning.
Yes, sir. It's all the learning process what we are facing in our life every time and anytime.
Yes.
Okay, so now it's 3:02. Now I will start the session.
जी, जी।
Good afternoon, all the participants, organizing members, and keynote speakers. I, Dr. Ravindra Kumar Sahadev from the Department of Mechanical Engineering, UIT MDO Rohtak, welcome you to the third session of the AICTE-ATAL sponsored FDP on 3D printing and design. I'm extremely privileged to have the opportunity to address our speaker, Professor Abid Halim, who is going to talk about understanding additive manufacturing through its basis. The session will create a more clear view of the additive manufacturing. We have no words to explain the excellence and achievement of our legendary speaker, Professor Abid Halim, in the field of 3D printing. He has H index of about 38 in Google Scholar and more than 25 in the Scopus, and more than 5,636 publications in as per the Google Scholar, and more than 153 articles indexed in the Scopus, and 310 research articles overall. And he has published 3 books. He has been founding honorary director, internal quality assurance cell, IQAC cell of the university, and headed mechanical engineering department and MBA program at JMI. Dr. Abid has also been an honorary visiting professor to IIT Delhi. Presently, he is regional editor, Global Journal of Flexible System Management, Springer, associate editor with JCOT, Elsewhere, and iScholar. He has undertaken consultancy work with DFID, Government of Odisha, EDCI, etc., and worked as a High Court appointed arbitrator for the construction project at DIAC, New Delhi. He has also executed various research and support projects of DST, AICTE, and UGC, and completed FIST funding. Presently, he works as a professor of mechanical engineering, JMI, a central university by an act of parliament in New Delhi, India. I request all participants to keep their audio and cameras off. If you have any queries, please put it in the chat box, and we shall discuss the doubts at the end of the session. I welcome sir to share the valuable knowledge. Sir, please.
बहुत बहुत शुक्रिया।
Thank you, sir. शुक्रिया, sir.
और ये अच्छा लगा देख के, आपको अच्छा लगा, और वो कॉलेज की बिल्डिंग देख के अच्छा लगा।
Sir, actually this was
बहुत दिनों से बिल्डिंग नहीं देखी है भाई। We have not seen the building. Other college, I've seen my own building, but not others' building. So to see the building, and this is good.
Definitely, sir. Yes, sir. Infrastructure of MD University as well as the UIT is very fantastic. If you have any time, please visit. Do visit. We shall be always be privileged, and we'll be happy to see you here to give us your blessings.
Obvious,
Please, sir.
obvious. I will love to come and see. And I have
Yes.
come to your place also. I think
Yes, sir.
your Punya Sahab was a good friend of mine.
Yes, 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 definitely.
I think,
Yes, sir.
I
At
think
the
we
time,
should start. We should start the presentation.
yes, sir. Yes, sir. Yes, sir. Please share the
And
presentation.
I'll also use some videos also.
Yes, sir. Definitely.
And to start, I'll just start my. I'll just start the presentation and then I'll go for a video.
Yes, sir. Definitely. Sure. Yes, sir. We have got the presentation.
Ah, yeah, yeah. Good afternoon, my dear participants. I think I'm audible. In between, if you find something, you can just.
Yes, sir. You are audible perfectly, sir.
No issue. Then
Thank you.
today my talk is on the very basic topic, understanding additive manufacturing through its basics. I am a person of industrial engineering, started with systems, went to BPR, then to supply chain, innovation, then I came to the additive manufacturing. The interest in this topic and in this subject I developed in 2010. And I wrote a letter to DST for FIST funding. They gave the funding, but in 2 years I got around 1.5 crore rupees, of which 1 crore was only given to me. And we purchased a additive manufacturing machine and a scanner and a software. At that time I had no publications, but I knew one thing, that this technology, this technological application will going to revolutionize the way we see the manufacturing. And I saw that how the Obama, when he became the president, he made a target for the industry to achieve certain standards in additive manufacturing. So I learned from him. I learned from the vision of those people that how they are going to change this world. This presentation is a very basic presentation, very basic presentation. Some of you may be knowing more than me. And this is about what is, how we achieve it, why we do it, where we use it, about additive manufacturing. Because when I see that people today, with the explosion of knowledge, they are not clear about the concepts of additive manufacturing. And what is additive manufacturing, what is not additive manufacturing, they are not clear about that. The vision statement of additive manufacturing was given by the Obama. And I don't want to go this slide. I just want to show you the contents. I have a huge content to talk to. It may take a lot of time. And here I am going to introduce you the additive manufacturing, the subtractive manufacturing, the difference. And then what is AM, its components, its platform, its process chain. Then I will elaborate the components. And in the components, I will go for the 3D printing part also. First of all, additive manufacturing is a process of manufacturing a product by layer addition of the material. Is a process of manufacturing a product using layer by layer addition of the material. If we compare this to other conventional manufacturing process, it offers a lot of benefits. People say it is environmental friendly, it is efficient, effective in design process, prototype development. All of you must be knowing about the concept of subtractive manufacturing. Subtractive manufacturing. जैसे if I want to manufacture a gear blank, I need to have a cast blank. I need to manufacture a gear, so I need a casting of the blank. To make the casting, what you do is that you need ingots. To make that ingots, you have to calcinate and sinter the iron ore, melt it, then make it an ingot. From the ingot, you make a casting. From the casting, you make a gear blank. From the blank, you cut it. You cut the blank through a cutter or a hob to get a respective shape. The shape that we desire. The number of teeth, the addendum, and everything that you want, you get it from that. To understand that to make a gear, we have been subtracting the material. So much iron ore taken, then ingot is made, lot of wastage. Then from the ingot, the casting, lot of again wastage. From the casting, we cut it again. So everywhere we are, and finally from the cast, we are making the gear by cutting. In manufacturing, we are subtracting the material to give the desired shape. This subtraction is done by a single point cutting tool or a multi-point cutting tool. You cut it. You cut at various places. You finish it. You super finish it. But everywhere you cut it. So what we do is, conventionally, we have a concept of subtractive manufacturing. Then I have a question. If you are an engineer, you can manufacture. Why can't you manufacture a plant? Why can't you manufacture a bone? Why can't you manufacture a human body parts? And there are many intricate shapes which we cannot manufacture with our present tooling, our CNC setup. No. So there is a need for a new technological platform that can complement our existing manufacturing. Complement. It is not a type of replacement of conventional manufacturing. No, you are not replacing the conventional manufacturing. You are just complementing the conventional manufacturing. Somebody comes to you, asks you, why can't you manufacture a house for me? Why can't you manufacture a road for me? Why can't you manufacture a pizza for me? Why can't you manufacture a heart for me? Why can't you manufacture a bone for me? Right? And I want to think of a design and I want to make that design instantaneously without making any dye or cutting. I just want to cut it instantaneously. How? So there is a big challenge. Now, the nature does the manufacturing and it does differently. You've seen the cells, they are growing layer by layer, they are growing. They are mutating, they are dividing. One cell divides to two, it grows. You have seen the trees, the rings grow. But our technologies don't do like that. And for engineers, the word is very, very, very big. Somebody, your son may ask you, Daddy, why can't we have a seed that if we sow that seed, we can get a gear blank? If we sow that seed, we get a job made of that. Right? We make a product, we make a bone, we make a stunt and put it in the heart of a child, stunt in the heart of a child, and it grows when the child grows. बच्चा बड़ा हुआ तो stunt भी बड़ा हो गया. You make a bone that grows. Why can't it is possible with us? I'm going beyond what I'm teaching. I'm just going beyond because I want you to dream. I want you to think beyond the conventional manufacturing. People should be clear that this type of manufacturing is not a substitute for your subtracting or conventional manufacturing. It is not a substitute. It's just complementing. So what we see that the natural conventional approach is not innovative enough like a natural growth. Your tree grows like, but we are not using those methods in our conventional approach. We need flexibility. I need every job to be different. I need everything to be shaped differently. For that, I need a different dye. No, it's not possible. Some products, it is just not possible. You have to make them standard parts, similar parts. And we have to be green. We need to reduce the material waste. You know that formalization, customization is coming with Industry 5, Industry 4. And there is a need for the product design development cycle time. You thought of a design, and you just want to manufacture it. That you are a production teacher, you have thought of a cup, of a glass that suits your ergonomics, suits your hand, it is a different design, and you want to make it. But your design will be very expensive to make by conventional methods. You want to make it a design just now. आपने कहा कि मेरा कप ऐसा होगा और आप उसको मैन्युफैक्चर भी करना चाहते हैं 5 मिनट, 10 मिनट, 5 घंटे के अंदर. You're not going to wait for the design. So we need to make a product, we need to manufacture a product that grows, that rebuilds, that resustains. अपने को खुद से सही कर लेता हूं, rebuild करता हूं. So for that we need a different technological platform. And here we come to the additive manufacturing. In additive manufacturing, I told you that it is a layer by layer addition. And the support system that adds to the additive manufacturing. That it is for the product development, it is for the rapid prototyping, it for the remanufacturing, it is for the rebuilding, that you need technologies. You need technologies that support in developing a new design. It needs scanning, imaging, it needs software support, it needs printing. So all these make you a additive manufacturer. So conventionally, when we started, we thought of printing only, 3D printing. But now it has become a much, much bigger area to think of. So specifically, AM offers 3 opportunities to us. Pehla, we want to redesign, we want to rapid prototype, and second is we want to make a product as near to the customer. Customer jahan baitha ho, wahan pe mil jaye. NASA spacecraft needs a repair. Spacecraft needs some repairs. But those repairs can't be made in the space. They can't take all those spare parts. So you need a technology where they can make a part in the space that is near to the customer. You make a part. And you make a part that grow. Like they are made like they are growing. So with this, the net effect is need for reducing warehousing, transportation, and packaging. So this is a slide where I am showing the 3 type of printing process. It is not AM, exact AM. First is your traditional manufacturing. We call it non-AM, traditional में. आपने क्या किया? प्रोडक्ट को डेवलप किया, ट्रेडिशनली ओवर द बोर्ड बनाया, ड्राइंग बनाई, फिर आपने इसका डाई बनाई, मैन्युफैक्चर किया, ठीक, और फिर आपने इसको असेंबल किया. द ट्रेडिशनल वे ऑफ मैन्युफैक्चरिंग, that you think of a product, you develop the design, you develop the facilities to manufacture it, and you manufacture it and you assemble it. What you do in rapid prototyping, that you are using additive manufacturing. You scan a product, you make its changes in the design, in the software, through a software, and through that software, you make changes in the strength, you make changes in the material also, material selection also, and then you have a 3D printer. From that you can print the product, and then you can finish it and you assemble it. This is the rapid prototyping systems. But in future, we need a digitally optimal design where we think of a design, we make an image file, we work on that file through a software, and that product is made by a printer, multi-material printer, which assembles also to this thing. So you think of a product, and that product is made through a machine in front of you. You don't need a setup, a manufacturing setup. You don't need a traditional systems for that. So this is what is our future. We want to go into DOD, digitally optimized design. So rapid prototyping was one area which used AM, and not AM, we call it 3D printing. It used 3D printing. Right. Now, I think I have made it a bit clear to you that AM is a platform of technologies which enables layer by layer manufacturing of a part और प्रोडक्ट. प्लेटफॉर्म क्यों बोल रहा हूं? इट्स कंसिस्ट ऑफ 3 प्लेटफॉर्म्स. फर्स्ट इज स्कैनिंग, इमेजिंग, इंस्पेक्शन प्लेटफॉर्म. सेकेंड इज सॉफ्टवेयर सपोर्ट प्लेटफॉर्म. थर्ड इज प्रिंटिंग प्लेटफॉर्म. Scanning and inspection platform, you have scans, MRI, CMM, CAD model, X-ray, CT scanning, and so on. All things, they give you outer surface scanning. Even ultrasound is also used here. Subsonic waves are also used here for scanning. And you scan an object. You think about an object. You make a model of an object. You make a physical measurement, and from that physical measurement you make. So that is data capturing. That is scanning and imaging, and inspection is data capturing. And then you need a software support. From that software you can change, you change your ideas, you see it on the screen, you simulate, and then you think how to make it. You want to set its strength, you want to see it's working, you want to see its assembly. Everything is possible through these available software. And after that, you get a file format that can be used for printing. Printing इसलिए बोलते हैं क्योंकि ये प्रिंटर की तरह से काम करता है, 3D प्रिंटर की तरह से काम करता है. And there we can have 3D printing, 4D printing, 5D printing, hybrid printing, bioprinting, and so on. So they are all categories of 3D printing. So we have additive manufacturing is basically a platforms of technology. 3 तरह की बेसिक टेक्नोलॉजी जिसमें हम यूज करते हैं. तो ये बहुत सिंपल बात है. 3D printing is not additive manufacturing. 3D printing is just a subset of additive manufacturing. Scanning is a subset of additive manufacturing. Software systems like your Rhino, SolidWorks, Mimix, everything, they are used to develop a part, mature a part, analyze a part, and they give you the software support. So understand that additive manufacturing has now matured, and it is not just something about the mechanical engineer. It needs industrial engineers, it needs electronic engineers, it needs computer engineers, it needs biomedical engineers, it needs doctors, it needs physics people. Imaging में ज़्यादातर most of the people are from physics, and it needs material, it needs a lot of people from chemistry. So it needs, and then it needs a lot of algorithm design people from mathematics. So it is a multidisciplinary area. We should be very clear about that. It is a multidisciplinary area. So what we say, that if you want to make a product through AM, So you scan it, you image, you make an image of the product. Then from that image, you make a CAD model, you go for surface modeling, you go for analysis, you go for testing, simulation, or then you analyze, you reconstruct, you redesign, and you substitute the material. You are simulating through the material also. You are changing material X, material Y, material Z, because additive manufacturing has shown you a different type of material sets. जो हम लोग समझते थे कि लोहा लक्कड़ manufacturing is a part of, no, they have thought of new materials, carbon nanotubes, peak, epoxy resins, then very tough silicons. So they are a different type of material which have come up and which are now available for making products. Like your cells, body cells, they are a material. Bioink. So we get materials. Then from the CAD file, you change into a format of .stl format, and from that STL format, you give input to the type of 3D printing technology. 3D printing technology, करीब 50 तरह की technologies are available, 50 type of technologies. But some of them are very common and commercialized and available in our country. Generally, they get an input from this software. From that input, they add layer by layer and they print a product. Layer by layer printing. Sometimes you need a post-processing of the part or finishing of the part, or you need a joining of 2 or 3 parts together. So that is the post-processing. Sometimes you also need pre-processing also. So we say that the AM platforms uses scanning, imaging, software analysis, then printing, 3D printing. Why we call it 3D printing, I will explain to you when I will come a bit forward. This is a process chain that is create 3D CAD file, converging format, part, printing, then post-processing, and then implementing to the part. This is the process chain for a 3D printing. So first of all, I come to scanning. A very brief about that, scanning and imaging. Scanning is used to create a free-form 3-dimensional data in a form of point cloud or a triangular mesh. Scanning की बात क्यों हो रही है? I told you that I used a word rapid prototyping. Why? Earlier, the purpose of this additive manufacturing was to develop a prototype. और जल्दी से जल्दी prototype बनाना. तो rapid prototyping was our requirement. So we made a prototype, and as early as possible for that prototype, मतलब like you are in a spacecraft or you are in a place, isolated place, your handle of the door has broken. You want to replace. So what you do, that broken handle image is taken. That image you can work with SolidWorks. You can join it. You can make an improved handle, right? You can analyze that design also if you want to make a change in design. And after analysis and change, you see that this handle, if made with a certain type of resin or certain type of plastic, what is the strength will be? Will it be able to take that strength? You test the strength also using a software, and after that you give the input to a printer, required printer, the available printer. From that printer you will get exact handle, and that can be again put to use. आप उसको फिर से फिट करके आप उसको यूज कर सकते हैं. तो स्कैनिंग एंड इमेजिंग इज वेरी इंपॉर्टेंट. आप देखिए CMM is used, probe type CMMs are used where you have a probe. Now with the camera devices, it has become very easy to scan. Earlier we used to scan by laser lights. Now white light, blue light is used for scanning. Light comes on a surface and it reflects back, and then it is captured, and there you have a good idea about the shape and the intricacies, and dimensionally it is correct in microns. So you can scan an object in microns and you can get exact shape on your software through the cloud data. And this is you have used X-ray for bones imaging, CT scanning for bones, hard tissues you can image, and then for soft tissue you use MRI, magnetic resonating. So you have different type of scanning devices. ऐसा नहीं कि सिर्फ आप एक स्कैनर जो है आपके, जो आप इमेज के लिए आप सिर्फ एक ड्राइंग पे ही आप इसमें इमेज बना सकते हैं. इमेज बनाने के लिए you have lot of available technologies. Even ultrasound can be put for use for making an image. So 3D scanners, they can help rapid creation of implants. Implants means human body में body shape को prosthetics में, और cultural आप सोचिए कि any building that you want to change, you want to document. Architecture people are using this scanning, and you can copy any design. Jewelry scanning, you scan a design, you change the design, and any object of desire can be scanned. Even if you want, you respect your teacher, so you can scan his face, and after scanning you can have a three-dimensional view of his face, and that face can be stored. So 3D view of somebody can be viewed, and then from that scanning you get into AR and VR, augmented reality and virtual reality is new world which is opening to you, and this is something you should be able to visualize. So in manufacturing, we are using rapid prototyping, remanufacturing, manufacturing, designing. And here the thing is that we have very intricate parts or large parts also, like somebody wants to scan the home. आपने पूरे घर को स्कैन कर लिया और फिर उसके वॉक थ्रूज बनाए. वॉक थ्रूज समझते होंगे कि आपने पार्ट को स्कैन किया, उसके वॉक थ्रूज बनाए. यू वांट टू cut a segment of the part, X direction, Y direction, and you can move into the part. That is possible through the scanning. So this come to the scanning is one part. Second part is software support. So in additive manufacturing, there are a lot of softwares which are available for CAD modeling, surface modeling, for lighting, for product development, for product analysis, for material change. But here I am telling you some software which are particular to additive manufacturing. So AM softwares, they enable you 3D printing of jobs, design optimization, reducing manufacturing lead time, reducing cost of operation, and reducing the printing time. So these softwares are supporting your printing. AM softwares are supporting your printing. It takes the CAD data and it optimizes that data for printing process. So building the print, the part, it helps you to see that the part should not fail, and workflow of the build part making is also improved. So even for making jewelry or kapda, apparel, or large scale production of automobile, houses, it can tell you before that how you should use your printer, what should be. So these softwares, they are there. This is a new area which has come up, and there are some simulation software options for 3D printing, which I want to put it here because I saw that people may not discuss this thing in our FDP. So there is one software, we call it ANSYS Additive Print, which is used for printing technologies like selective laser melting or direct melting and laser sintering. This is ANSYS software. ANSYS is a company of US. So this simulation software is for validating the design of metal parts. Because selective laser melting is again a metal manufacturing process when you are manufacturing a part through metal. So it can help you visualize the fabrication of a part. You can go into insights, the potential distortions, and you can find out the residual stress, and you can it can help you in developing an optimal support structure, and even it can give you a very good distortion compensated STL files. This you will understand when you are going to print a job. STL files are the formats which are used for input to the printer, but here again distortion is there, and that distortion ko compensate karne ke liye, this is something which is very, very important. It improves the quality of the print. So it has suites like additive suite, additive science, and topology optimization, thermal analysis. Everything can be done by this software. Then there is flow science, flow 3D, which again binder jetting, which again supports the metal printing and binder jetting also. Binder is the liquid binder printing. And flow 3D is capable of simulating various aspects of 3D printing process. You can simulate fusion bed, you can simulate a printing, and you see that laser melting of powder, how it's going to melt, and the metal pool formation, solidification, and through that you can improve your product structure. It has a multi-physics approach to printing, and it gives you a very valuable process insight. Then there is a software, Extreme Digimat, which supports FDM. FDM is the most common technology which we are using, fused deposition modeling, and SLS, selective laser sintering. So this is software is very good software, and it has a material database. कौन कौन सा material we can use. It can help you the calculation of mechanical, thermal, and electrical properties of a material. It can tell you warpage is happening, where it's going to happen. So these softwares are basically simulation softwares, and before anything happens in the printing, before that it's going to tell you. This is the beauty of this software. So the best part is ability to analyze part performance. जो पार्ट आपने प्रिंट करने जा रहे हैं वो परफॉर्म कैसे करेगा, and how you can change the orientation. You can change the orientation. It can improve the your part manufacturing. So it can tell you where to put your part, x-axis, y-axis, z-axis, z-y-axis. So it is going to guide you. So this is something, it gives you the good idea about the printing orientation and where to print your job. And it has a material database. And it gives you idea also कि आपका job will be good or the job that you're going to print will be a bad job also. This is something which is used for. Then Simofact, additive supported technologies. Then there is an Autodesk, NetFab supported technologies for the metal printing and 3D printing. It's a simulation tool that helps you the thermal and mechanical to predict the thermal behavior and the mechanical behavior of the part. It can identify the deformation in the virtual environment, and it is available. Most of these softwares are available in cloud. So Simula is one software from the Dassault system, and now we come to the CAD process. The CAD process, you know that CAD process is, I'm telling you the software part of that. The CAD process, you do the synthesis, you do the analysis. Synthesis is qualitative, and then analysis is generally done with the computer. When the analysis is complete, you do the design evaluation, and then you go for a printing of the job. So you have 2D CAD, and then you have a 3D CAD. That we have seen the wireframe models. Like from the wireframe models of a car, and then from the wire mesh, you make a surface modeling also. You can look at the shape of the product, and then you can analyze that product, different conditions, right? And you can have a solid model. You can know the shape, the area, the volume, how the product is going to function also. And this is something the CAD can help you. And CAD modeling, through most of you must have used SolidWorks and ANSYS, and you know that how beautiful the SolidWorks can make a surface modeling, and ANSYS can analyze your products. So from the CAD CAM, that you know that the CAM, traditionally from the CAD model, we make the CAM, but from the CAD part. So just a small brief about medical science also. Why? Because I may tell you that in last 10 years, what I saw, that this technology set of AM, this platform of AM has grown more for medical science than less for manufacturing science. Manufacturing science already has lot of conventional systems, and they are cheap to make. And in medical science, the requirement is huge Doctor wants you to print a head, a bone, head, skin, everything. Huge area is there, and but and they have money also. If you go to a manufacturer, he will say that how cheap I can make a product from this technology. He will talk about cost reduction. He will talk about material reduction. While in medical, the doctor will tell you how it can take up the challenge, how it can reduce the human suffering. Human suffering, right? So this is how they think differently. Human suffering reduction has there the person do not consider any cost. Understand this thing that they want to just get their suffering reduced. The cost is not an issue. So when the cost is not an issue, the development comes here. What I see that in future, 10 to 20% of the engineers will working in the hospital. They're already there in the hospital. They're running all those imaging and software devices and everything. I have seen that in AIMS, the students are learning sciences, they are learning your technologies, and they are now using those technologies. Simulation has become very important for them. I have seen their anatomical table, which is basically an AR VR table. So understand that what is happening there. The engineers has come out from their manufacturing of just car or this traditional things to the support to the human systems, support to medical sciences. They have come as a support to natural science people. So they have come out of that, and they have huge requirement there, not only in this industry. So what we see in medical science, that CT and MRI data is used. Then from that data, we use software like Mimic, Slicer, Magic, Doctor. They're very expensive softwares. I've seen them, and they tell you that how to convert the CT data into a 3D model, CT data. And from that CT data, 3D model, then you can make an implant, you can make a part, and then you can print a part, and then you can put into a human body. So this is something, just if I get time, I will discuss about how beautifully they do it. So, nice area. That is in the important part of this software support is not only simulation or analysis or data capturing or surface modeling, but it is conversion to printable format. Conversion to printable format. STL is one of them. STL format can be directly put to printer and it can print. STL format इसलिए होता है because it gives you slice data and that standard triangulation language format. So that language is taken by the printing machine and they can fabricate the part from this format. So, right, the product designing. So, manufacturing of parts through 3D printing. So you can technology is used to fabricate 3D physical model. You can by adding layer by layer, and AM we are using to create a 3D physical implant, 3D CAD model. Then CAD model is analyzed, then it divided into thin cross sections. Then this cross section are fed into federal format, and then you make a part. And this technology is very useful for prototype development, for product design, for customization, and for providing a better idea to part production. And you can make a complex shape and show. So we come to the printing technologies. Before coming to printing technologies, I just want to come back to this my lecture, and I will invite any questions that anybody wants to ask, because this is fun. I think I am audible to everybody, right? You can ask some questions before I come to the second part of my lecture. Any question, please? I think it's something, anything that you want to ask from me?
Hello.
No, yes.
Sir, we can take the question answering session at the last, sir.
अच्छा नो इश्यू ठीक ठीक होता क्या कि when we teach and we see that nobody is there in front of us because we
Yes.
are teaching, what I see that there is nobody. When I feel that कि आपका जो है layout is something, I'll just do one thing. I'll change my layout to sidebar, so at least I can see the people also, right?
Definitely, sir.
है ना? तो ठीक है, I'll just again go back to my presentation.
जी sir, please.
ठीक.
जी जी sir.
अच्छा, first thing that there is no feedback ना, तो क्लास में तो मालूम होता है कि बच्चे उठ के चले गए, आ गए, और कोई सो रहा है, कोई मुंह बना रहा है.
Sir, for your response, I tell you that 84 participants are joining from this Google Meet, and more than 40-50 students participants are through the YouTube link are
so
also
nice.
there. Definitely,
So nice.
we have generated both the platforms. If anybody cannot join this Google Meet, can also watch this complete session recording at the YouTube, and it can go at the live.
अच्छा.
You can please carry on, and we shall take the question answer session at the end of the session, sir.
चलिए सर, जैसा आपका हुक्म.
Yes, sir. Thank you, sir. Thank you. जी.
छोटी जगह 10 के हिसाब से पूरा हांगकांग बंद कर देता हूं। ये इंडिया में तो नहीं देते हैं। कोई आके लगा गया तो भाई बंद है। ये जो छोटी कंट्रीज है मीडियम ले जैसे वहां पे जाएंगे। शुगर आप देखिए तो सिंगल में हांगकांग वैसा है ना कि एक आदमी निकलेगा तो उनको 100 आदमी से मिलते हैं।
I think I'm not just
Participants, please mute yourself.
No issue, sir. No issue. Just I'll just go through a very brief about the
Yes, sir.
3D printing technology.
Yes.
So what I have briefed was about the additive manufacturing platforms. And additive manufacturing platforms, I've told that about the scanning and inspection platform and imaging platform, one, then the software support platforms, and the software support platforms. The important part is the AM softwares, which basically simulate the printing beforehand. Printing is done. And then we have 7 major printing technologies, 3D printing technologies, which are commercialized and are available in India also. They are through their various international partners. And this major ASTM standards, they define that there are 7 type of AM printing technologies, like VAT photopolymerization using light source to harden liquid, then binder jetting, liquid bonding agent with the inkjet print head, then energy deposition, material exclusion, material jetting, powder bed, and sheet lamination. I will tell them a brief about all of them, very brief, because I can't give justice to one technology even if I talk about an hour for about them. So this is very common technology. VAT photopolymerization. I think I'm visible, audible, and
Yes,
visible both.
yes, sir.
And there is no what you call it uh, distortion or noise. There is noise, something, no noise from my side.
Oh, we are getting you, sir. We are getting you.
No issue.
Okay.
Ibrahim. Acha, first of all, I come to the VAT photopolymerization. Photopolymers, you know that photopolymers, they have very important role, and these photopolymers, they are photosensitive resin. So these liquids, when they are fed with ultraviolet light, they harden and they take a shape. They harden. So this hardening, we call it curing. Curing. So they cure or harden when ultraviolet light falls on them. VAT means a box or container which contains this photopolymer resin. So we can develop a platform, and we can accordingly move our printing head on this photopolymer, and this photopolymer will harden at the place where the ultraviolet light falls, and it can get a shape. So this is a very old technology, and it's very much used in making beautiful shaped intricate parts. uh, Stereo photo, this is something just I want to show you.
Sir, we cannot see the presentation.
Just a minute.
Is there any problem, sir?
No. Just
Yes. Okay, okay, sir, please.
sorry. What we have done is, I have used uh, एक मिनट
Yes, sir, please.
just a minute. What has happened is, I am not able to. Hmm. Is this video not visible to?
Sir, your screen is not visible. You please share this.
Yo,
Definitely. Yes, yes. You share the screen.
No. I just.
yeah, screen is visible now, sir.
No, what has happened now? This is video is in Chrome, not in Chrome. It is some other format, and then it is. Are you able to see this
Yeah, I can see this time.
video?
Yes, sir.
Video.
Let's go to see. Yes.
Yes, sir. Video is visible.
So we come back to the stereolithography, and that we call it VAT photopolymerization, and we have seen that how beautifully it can make an intricate part. This is, you have seen that a laser or a ultraviolet light source can be used, and there can be multiple light source. So today we have seen a lot of changes here in this technology, and there is an instant printer also, where in one go a 3D model can be made instantaneously. Just at three projectors are placed, and with the help of three projectors, light is put on a vat of resin, and that resin cures with the light, and you can take a 3D shape also. This is a technology which is coming up, and it is being used by many companies. Even Maruti also, they are for making their first part. They use this technology of wet photopolymerization. We call it stereolithography. Second one is material jetting. Material jetting technology sets, like again, it creates an object in a similar method as like a two-dimensional inkjet printer. You have seen that inkjet printer. There is a printer head, and from that printer head, there are small jets which throw color on a piece of paper, and ultimately it uh, uh, prints the paper. So here again, the material is jetted through that print head, and this material jetting is done on a platform, a built surface, and there this jetted material solidifies. And when it solidifies, and again layer by layer it solidifies, you get a shape. So material jetting is done through a nozzle, and that nozzle, it moves in XY direction, and the platform moves in the Z direction. So we also use the UV light or a curing light for this jetting. So you have seen that the UV lamp and a blade is there, and the built material and the support material, both materials are there to create a shape. Built material is to create a shape, and support material is to support that shape. Sometimes in printing, the shape is such that it cannot sustain on its own. So warpage can occur. So there you have seen that this is the material jetting process. And with this, you have seen that there is how the resin is jetted and how the curing light falls into this resin. Right? So material jetting is one technology which has come up, but since I don't have time, I'll just move fast. The third one is binder jetting. Material jetting is not very popular, but binder jetting is popular. And binder jetting technology may here we used a binder which falls on a powder. So that powder, when it's when the powder it mixes with the binder, it takes a shape, a layer shape. So this binder, it acts as a adhesive between powder layers, one layer of powder, another layer of powder, and then you jet a layer of binder on the powder, and ultimately your print head moves in XY direction, and your plunger moves in Z direction, and ultimately you get a printing. So binder jetting is a very successful printer, and they are used for generally for medical purposes. And here you can use what do you call it, bio compatible material here also. And binder jetting can go for making a colorful objects also. And but these objects, they can be cured, they need curing, and they need post processing also. So in the binder jetting, you can see the binder jetting process. There is the roller leveler, and that roller moves, and the powder layer is put on the platform, and on that powder a binder is sprinkled, and that binder, it interacts with the powder, and then again next layer of powder, then again binder, then again a powder, and this way you build a job. So binder, it has to come in contact with the powder, and ultimately you built a good job. And this printer, I have this printer in my lab, and we have printed good objects from this colorful objects. But the thing is that it's very costly, and the powder, generally these powders are uh, calcium sulfate and phosphate based material, and they are more a patent of the company, and they don't allow you to change this powder. Even the binders are very expensive also. But it is good if you want to print an intricate object, and especially the medical applications. Then you have a very common type of printing technology. We call it FDM, fuse deposition modeling. And FDM is the most common extrusion process, and it started with Stratus. And if you see, there is nothing big with these technologies. These technologies are all 30, 20 years back, old technologies. Here you have a nozzle, it is heated, and then it is fed with a plastic or a substance, and that substance comes out as a sludge, and that sludge falls on a surface, and this movement of the head is controlled, and ultimately it gets a shape. The nozzle, it moves horizontally, and the platform moves up down. This technology is very, very simple, and you see then you will see that this is what it is. A material spool is there. Material spool is there, and that material spool feds the wire, and that wire goes to a heater element. It melts, and then it is with the help of a nozzle, it is put on an object. It is put on a platform, and that platform melts, and then this platforms moves ups and downs, and ultimately you can build a 3D model. This is the better printer, which also has two printing heads, which has one more printing head, and one printing head is for support material and one is for printing the job. So we need support material because sometimes the job is such a shape that it cannot sustain its structure on its own. So you need a support material also. So build tray and the platform, it moves in the Z direction, and the nozzle head, it moves in the X and Y direction. This is how this here I'm telling you, this technology has evolved with time, and people are also now using they're printing glass, ceramics, and metal through this FDM process. Glass, ceramics, and metal. What you need is a very good zirconium nozzle. You need a high quality nozzle which can take a very high temperature pressure, and then you can print any object. And then the enclosure is to be evolved. And this seems to be very simple technology, but when you develop technology for a very special type of application, that becomes more and more expensive. So simple FDM printer, industrial type 10-inch printers, they cost around 15 lakh rupees. So FDM printers are very common, and they have into the learner new idea printers, idea series. They are very cheap, 40,000, 50,000 rupees. You can get a good printer, and but they have open source software. Then you have design printers. You can print your prototypes, and then you have industrial printers which are coming. Design printers are desktops, 5-10 lakh rupees. Then industrial printers they come to very expensive, 15, 20, 50 lakh rupees. So this is very common type of printer. I think everybody in their schools, they are teaching through this printer. Even I have bought this printer in my home, and we are using it for then the fifth one is the powder bed fusion. Powder bed fusion, that is powder on a bed. You put a powder, and that powder is melted either by laser sintering or electron beam, or by heat sintering, or by selective laser, right? So you can melt a powder, SLM. You can sinter. Sinter means lesser intensity of heat. So there